So this is a big subject. This talk is mainly based on two papers, both from my graduate student, Rudin Petrosian-Bryn. Here he is. This is the first one, which is already out in the archive, which is QCD flavor in the de Sitter swampland. And then there's a second follow-up one, which is more to do with the Higgs sector, which is the standard model in the de Sitter swampland. Rudin is yet another one of my superb students. So when he applies for jobs, postdocs in a year's time, please hire him. Also, many thanks to many other people I've had important conversations with over the years on swampland issues. So thank you to them too. So the Swampland Program, you all know, but let's just summarize very quickly. This is the idea that not all effective quantum field theories remain consistent when embedded in a theory with quantum gravity, or rather, not all theories can descend from a theory of quantum gravity. And so the modern incarnation of this idea is due to Vaffer and many co-workers. And of course, the idea is there's a swamp of apparently consistent effective quantum field theories, but only a smaller and possibly much smaller landscape of consistent quantum field theories with gravity. And so, of course, it's good if we have restrictions on possible energy effective field theories. We used to believe that normalizability many years ago was a crucial requirement for consistency. Now we understand better. But if we have new restrictions, that's great. That helps us a lot. So, of course, at present, most of these suggested criteria take the form of conjectures, often with unknown order one constants appearing and having varying levels of support. So if you go through this list, it's an ever-growing list. As we'll talk about, probably the strongest supported one is the no global symmetries conjecture. But then there's a weak gravity conjecture. And then there's other ones go down. In particular today, I'm going to be talking about one of the newest and one of the most controversial in a sense conjectures, which is the refined de Sitter conjecture. I'm going to show you this. If this is true, this is actually a very powerful restriction on low energy theories. So the major question that I care about, I'm an effective field theorist, I'm a beyond the standard model theorist. My question is, I want to understand what impact does the Swampland program have on our understanding of the standard model, if any. That's the crucial question. So let's think about the first thing, which is the statement there are no global symmetries. So this is the oldest and best supported of all the swampland conjectures. Actually, it goes back really to 1957 with Wheeler, but also Hawking in the early 70s as well. And the idea is that in a theory of quantum gravity, you cannot have an exact global symmetry. This has been extended in recent years by the weak gravity conjecture, which says, among other things, that you can't realize a global symmetry as the zero coupling limit of a gauge theory. But also this paper actually has some other important statements that we will use going on along the way. So there's much evidence in favor of the no global symmetry statement, including in ADS backgrounds, a proof using ADS CFT techniques by Harlow and Aguri just last year. So I think very many of us would be greatly surprised if this conjecture didn't turn out to be true. But the question is how does this impact standard model phenomenology? And what I mean by that is how to help us understand features of the standard model that otherwise may be mysterious. So in fact, it already tells us something quite remarkable about the standard model parameters. I want to emphasize to you that the standard model has, in the absence of Yukawa interactions, a non-anomalous global flavor symmetry, which is quite large. It's SU3 acting on the left-handed quark doublets, SU3 on the up, cross SU3 on the downs, cross et cetera, and then maybe further symmetries. Probably there are flavor symmetries, of course, in the neutrino sector. So the claim is the embedding in quantum gravity stops us taking two or more Yukawa couplings of equally charged matter fields equal. This is very striking that it's quantum gravity that is stopping us taking, for instance, the up-like Yukawa coupling and the charm-like Yukawa coupling equal. That's an example that's going to be important to us later on. This is fascinating. And of course, it's completely consistent with observations. In fact, we have no unbroken global flavor symmetries like this in the standard model. But it's only if the restriction is if only exact equality is forbidden, then in fact it's not very useful. So the question is does the no global symmetry statement say only exact equality is forbidden? Well, in fact, there's a recent Swampland global symmetry conjecture, which says that there's likely a larger part of parameter space which is carved out by the no global symmetry statement. So this is asking how good can an approximate global symmetry be? Is there a sort of lower bound on the amount of symmetry violation that has to occur? This is by Fichet and Sasarawat in 2019 in a paper with myself and my Heidelberg collaborators just a few months ago. So Fichet and Sasarawat had a thermal argument involving black holes. They say that in a thermal bath at temperature T, less than cutoff, the rate of global symmetry violation should satisfy what they call a local rate bound. And this is a statement: the rate of global symmetry violation in the effective field theory due to global symmetry violating operators should be strictly greater than that due to black holes. And the black hole process is I have some thermal fluctuation in my backbound plasma. It produces a black hole, which then Hawking evaporates. And in this process, you change barrier numbers. So here is one where it just happened to be a thermal fluctuation. We had barrier number initially n. Well, the biggest you have at the end is plus or minus square root of n, just by the statistical independence of black hole, Hawking evaporation in this case. So the question is and this provides a lower bound on the strength of global symmetry violation in the effective field theory. In fact, there's another argument, which is due to myself and, again, my Heidelberg collaborators, which is a weak gravity conjecture-based argument for gauge-derived, a particular subclass of global symmetries, gauge-derived global symmetries. And this says, effectively, that if you have a world line of a particle with global charge, there always has to exist an instanton that terminates this world line. And when you integrate out these instantons, you get in the effective theory a global symmetry violating interaction. Here, phi is the global symmetry carrying field. And so this is a delta phi equals 1 operator. And it has a coefficient, e to the minus s, this instanton amplitude, which in fact you can bound using Greek gravity conjecture arguments. So I don't have time in this talk, because I want to talk about something else mainly, to say where this comes from. I could in discussions maybe later. But it says there's a lower bound, which goes like e to the minus c, where c is some unknown order 1 coefficient, m Planck squared over a cutoff squared. And interestingly, the cutoff squared is not just a new particle mass scale or something like that. It's a much more serious breakdown in the effective field theory. It's related to a string tension. So this is when strings are effectively becoming light, the scale at which strings are turning on. So this is a very interesting bound. But the issue is, sorry, I just want to get rid of this thing. But the issue is this useful? Well, it was better than before. All right, because it's not just exact equality we bound now, but unless we can argue that this cutoff lambda is very close to M Planck and also fix this coefficient C, make sure C is not in fact 100. This weak lower bound of global symmetry violation still only forbids an exponentially tiny region of parameter space. So it's no longer the upright Yukawa coupling and the Charmiot Yukawa coupling being exactly equal, but now they're forced to be slightly different from each other, but only by this exponential amount, unless we can prove independently that lambda has to be large, close to M Planck. So the question is can we do better? And my answer is yes, we possibly can if we turn to a different swampland condition. So this different swampland condition is the Swampland de Sitter conjecture. So this is one of the most striking, and also I would claim one of the strongest of all the conjecture constraints on effective field theories coming from the theory with gravity. So I'm going to tell you about what's called the refined Swampland de Sitter conjecture. This is due to two recent groups involving Comron now. And so this says that there is a constraint on the derivative with respect to field directions of the potential, the total potential of all bosonic fields in my theory. This has to be bounded below by the value of the potential over M Planck. And there's also, or there's a constraint on the curvature of the potential. If the first condition is not satisfied, then you can look and see whether you satisfy the second condition. So either you are on a slope, which has a bounded slope, or you can be at the top of a maximum, but then you have to be a curvature down. So the important thing about this is it says, among other things, that potentials with metastable de Sitter vacua are in the swampland. As are regions of field space that are too flat if if you're in a region where the potential is greater than 0. So this is a really strong constraint. It's a remarkable constraint. And there's some evidence for this. But there's also some arguments against as well. So I think it's fair to say this is controversial at the moment, with both arguments being made for and against. Here, I'm going to simply assume that this conjecture is true as stated, and I'm going to investigate the consequences of this conjecture. So obviously, not surprisingly, the dominant use so far has been in early and present cosmology. I'm going to make in particular the claim that plausibly the Swampland de Sitter conjecture limits the flavor structure of quarks and maybe even sheds new light on the hierarchy problem. So that's going to be the topic of the rest of my talk. So I'm going to talk about metastable states. So here we're going to start off with a well-known story that goes back to the early 80s, which is the metastable states of QCD with light quarks. So it's in fact well known that for more than 2 light quarks, the Chiral-Lagrangian predicts metastable states. This is originally due to Witten in 1980, and then there's lots of follow-up papers, but in particular there's 2 very useful ones by Kreutz and Smilge. So since this phenomenon is core to our claims, I want to describe this in detail. And then we'll also look at lots of generalizations of this. So let's consider SU3 QCD with N-light quarks. So this theory is still confining and chiral symmetry breaking, as long as N is not large enough. And so the chiral symmetry breaking is the standard chiral symmetry breaking SUN left cross SUN right to SUN vector. So the low energy physics is determined by the pseudo-Nanbuhr-Goldstone Chiral-Lagrangian, where we have at leading order a kinetic term, which is the trace of the Callan-Common-West-Zumino parameterization of the pion degrees of freedom. So here sigma is the exponential of all the light pion degrees of freedom. Ti are the generators of SUN. And so the very first term here is the kinetic term of all the pions. And of course it involves an infinite series of interactions which are completely fixed by this non-linearly realized symmetry. And then we have a mass term, which is going to be very important to us. So there is a dimension 3 coefficient B0, which is set by QCD dynamics, but which is of order lambda QCD cubed. And then it's the light quark mass matrix, an n by n light quark mass matrix, which we can take diagonal without lesser generality. You can show that. And it interacts with this sigma by this trace term. So we get a trace of MQ dagger sigma plus the Hermitian conjugate. And what I've done is there's a possible theta term here, which as you see is also going to play an interesting role. I've allowed the possibility that the QCD theta angle is non-zero. So that means the whole thing, theta bar plus arg det n, and I've pulled that out explicitly because that's going to be useful to us. So let's look at what the vacuum structure and metastable structure of such a theory is. So, as I said, you can take the quark mass matrix to be diagonal without loss of generality, and I'm going to order the quarks such the heaviest one is M1. I want you to remember this is a slightly unusual convention. M1 is the heaviest, Mn is the lightest. And so I have those n mass parameters and 1 theta angle. But in fact, this is a problem where you can scale out an overall scale, factor out an overall scale. So it really depends on n parameters. So what we're going to look for is we're going to look for all space-time independent extrema of the Chiral-Lagrangian potential. And I claim they're always of this form. They're always of the form some e to the I theta bar over n. That's just factored out for convenience. Then a bunch of phases. The diagonal, sorry, this should be, it's a typo. These should be phases. Should be diagonal of e to the I phi 1, e to the I phi 2, e to the phi n. So these are just useful recombinations of all the vevs of the SUN Cartan subalgebra pions. And they have to satisfy a constraint that phi 1 through phi n plus theta bar is equal to 0 mod 2 pi. Okay? That comes just from the definition of what I mean by the theta bar. Okay. So that's my theory. So what's the potential? Well, if I substitute that thing into this Chiral-Lagrangian, and just the potential term, because it's space-time independent, and incidentally, the Swampland de Sitter conjecture is talking about boost invariant time-independent backgrounds. That's what it applies to. It doesn't apply to, for instance, a lump of iron, or other situations, or a thermal bath. It applies to situations where I'm boost invariant time-independent. So here it is. I substitute this in, and I look for the potential, and this is the form of the potential I find. It's minus B0, this mass dimension 3 coefficient, times the individual quark mass eigenvalues, times cos of these phases, and then the sum of those terms from 1 to n. And again, subject to the constraint that phi 1 through phi n plus phi theta bar is equal to 0 mod 2 pi. So in this way of thinking about it, to every quark mass, an angle is associated. Moreover, you can show very easily the condition for a critical point is given by this tower of identities. There's a tower of identities, and what I want you to notice is this relates sine of the various angles up to quark mass ratios. So what's crucial here is the quark mass ratios is going to come in. So in fact, you can understand all the analysis I'm going to give by a beautiful method, fan diagrams, actually the Rudin, my student, invented. And I recommend you look at the paper because you can understand everything geometrically. You can understand when you have critical points and what the nature of the critical points is, whether they are local minima, saddle points, or local maxima, purely by looking at the geometrical properties of these fan diagrams. So that's very nice. Of course, we care about local minima, so we compute the Hessian around these critical points. And a necessary condition for positive definiteness is that cos of these angles phi I is greater than 0 for all I less than n. Okay, so that's the condition. That's a necessary but not sufficient condition. So it's very easy to go and study this set of vacua, the various branches. And what do you find? So let me give you some intuition. Let me tell you about the simplest case, which is equal quark masses. So here, if you have equal quark masses, then it's easy to show the critical point condition plus the necessary condition for positive definiteness plus the unitarity condition, which is again phi 1 through phi n plus that sum plus theta bar is equal to 0 mod 2 pi. It's easy to show that all these phases must be 2 pi times an integer minus theta bar over capital N, where capital N again is the number of light quarks. And so it's all common phase, and this n is an integer. And finally, if you look at then the Hessian matrix around these critical points, you find it's positive definite if you can satisfy this following condition. So this integer little n is in this range, minus n over 4 plus theta bar on 2 pi is less than n, and n is less than n on 4 plus theta bar on 2 pi. And so just staring at this condition, you immediately see that for n equals 2, n greater than 2, there's more than one integer in this range, and therefore metastable states definitely exist. This is only depending on the leading order Lagrangian being reliable. So as long as the sub-leading terms are small, so as long as the quark masses, or the light quark masses are sufficiently small, that's always a good approximation, and this is reliable. Okay, so what does it look like? What does the state structure of, say, 3 equal quark mass QCD look like? So what it looks like is the red lines here. So this is as a function of theta bar, because the quarks are all equal mass. The only control parameter we have in this theory is theta bar. And so the red lines here give you local minima. Okay, the green dotted lines are saddle points, and the black lines are local maxima. And what I want you to notice is there's a range of theta bar around pi, and also of course minus pi, where you have 2 red lines. There are, at any place, there's 2 local minima. There's a true ground state branch, and then there's an excited local minimum branch as well above that. And they're split from each other, unless you go very near the crossing point of the red lines, they're split from each other by an amount which is of order the quark mass, which again is equal in this case, times lambda QCD cubed. Okay. So, all right, that's what's said here. All right, saddle points are green, local maxima are black, the local minima are the red lines. Right. So this is so metastable states exist in this range, which is theta bar that goes from pi on 2 up to 3 pi on 2. Right. So in this case, not including theta bar equals 0. Okay.
Do you mind if I ask a quick question?
Yeah, please go ahead.
Is this crossover of the 2 vacua the same crossover discussed in like the papers on anomalies in the space of coupling constants?
Very possibly, yes. I mean, so it's strongly related to a phenomenon called Dashian phenomena, which is an old thing, which is breaking of CP.
Sure, yeah.
Around these things. So yes.
Great, thanks.
Yeah. Incidentally, you can study there's a very rich set of questions you can study very explicitly using the Lagrangian around those points. In fact, you have a lot of power, and you can actually understand a lot of things that are in recent, Natty Seiberg and other papers, right, by studying this point. Anyway, so let's do a more complicated case. Let's do 4 quarks in two equal mass groups. So now there are two control parameters. There's theta bar again, which is on the x-axis of this graph, and then there's a mass ratio M3 or M4 divided by M1 or M2. Okay, and I remind you again, M1 is the heaviest of all the quarks. So this mass ratio is less than 1. And what you find is the entire red portion of this diagram, metastable states exist, and they don't exist in the white portion. So an order 1 amount of this parameter space has metastable states. So what we're going to argue, and I'm going to fill in more and more details as we go along, is that all the regions of parameter space with metastable states are plausibly excluded by the Swampland de Sitter conjecture from descending from a theory of gravity. Okay, and I'll tell you more and more details as I said to go along. So that's very striking. I want to emphasize that, again, this is an order 1 amount of parameter space. And I'll show you yet more plots about how much a parameter space can be carved out. It's not exponentially small, it's order 1. So what about the observed standard model parameter values, the 3 quark-like masses, and theta bar equals 0? Okay, so here is the plot. This shows experimentally that situation. 3 light quarks, we have 2 mass ratios, and we also have a theta varying. And the standard model is the little tiny red dot down in the bottom left-hand corner. And the green regions are the metastable state regions as a function as we're varying theta. And it's always the case that as you turn up theta bar towards pi, the metastable state region increases. And as you turn it down to 0, the metastable state region decreases. Later on, you'll see an example where even at theta bar equals 0, there are metastable states. So the standard model is consistent with, and it would be consistent at any value of theta bar with no metastable states. Amusingly, you can look at the condition. The theory is safe from metastable states for any value of theta bar in an N-light-quark theory. And that's the condition where 1 over Mn is greater than the sum of 1 over M1 up to 1 over Mn minus 1. And this is satisfied by these light quarks. Again, just as shown in the previous diagram, 1 over M up is greater than 1 over M down plus 1 over M strange. But crucially, if we had, say, 5 or 6 light quarks with not large mass ratios, then we would have metastable states at theta bar equals 0. So here is a picture of what goes on. So here is this more complicated case. This is 6 quarks in 2 equal mass groups for theta bar equals 0. So now the control parameters on this plane are just the these 2 mass ratios. All right, you have just the overall, and here, there's one control parameter. There's the mass ratio. Everything else, theta bar is set to 0. There's the 1 mass ratio that's on the x-axis, and here is the potential function with lots of branches. So what I want you to see is, I want you to see that once this mass ratio, that there's 2. This is just a tiny selection actually of all the states that are there. So the dotted lines are saddle points or maxima, but the red line and the solid blue line are a local minima. Right? So once the mass ratio is above about 0.5, which is again on the x-axis, once it's above 0.5, you have two local minima states. You have metastable states that exist in this theory, and this is even for theta bar equals 0. So in this case, again, roughly half of the parameter space is excluded by this condition. Okay, well, all right. Okay, so what are we assuming here? So we're making some assumptions. We're assuming that the ground state is near 0 cosmological constant. Okay, and we're assuming the excited state, this metastable state, right, is high up into de Sitter space, right, by an amount which goes like the quark mass times lambda QCD cubed, right? That's that. If certainly if the ground state is near 0 cosmological constant, that's true of this metastable state. But so far, we haven't addressed a very important question, which is how the Swampland de Sitter conjecture is consistent with our presently observed cosmic acceleration. So, assuming the Swampland de Sitter conjecture is correct, I'm aware of at least 3 possible responses to the observation of cosmic acceleration. So the first is the cosmic acceleration is not due to a cosmological constant, but it's instead due to an evolving quintessence field. A possibility, which is shown in this paper by Pratik and others, which is marginally consistent with data and the Swampland de Sitter conjecture. There are 2 other possibilities I'm aware of. Another one is cosmic acceleration could be due to so-called thermal dark energy. This is an effective energy density due to unusual thermal effects in the hidden sector. This is not in conflict with Swampland conjecture, and this is due to Ed Hardy and Paramecium in Liverpool. And then there's a heterodox view, which is unlikely in my opinion, but I want to emphasize it's not logically impossible, that either the cosmic acceleration is not what's being truly observed in the data, or the far infrared theory is not GR. So to be conservative, and also because it's most potentially deadly for the ideas in this talk, I'm going to assume that it's point one that's true. I'm going to assume that we have quintessence around, so it's an ultralight field, and this is deadly for what I've said so far, because potentially it can destabilize local metastable minima and nullify our results. Certainly, we're assuming that the ground state branch is in this slowly evolving slope down, down to 0 CC. Right? So what about the excited? Could we also have quintessence solve, or some version of quintessence solve the problem of these excited states? So let's add an ultralight quintessence field to this model and consider two general possibilities. So there's two possibilities. We can have a sequestered form for the potential where the quintessence field phi is basically decoupled from the QCD sector and the pions, or they could have significant cross couplings. And here, these Y alphas are all the standard model parameters like quark masses and the theta angle, and N are the various branches of this potential. So this is again a multi-branched system in QCD. So now you have to enforce the Swampland de Sitter conjecture conditions. And we have to see whether successful quintessence potential is consistent with these. So let's do the sequester case. So here's a rather busy diagram. So the solid black curve at the bottom is the ground state branch, which is very close to 0 cosmological constant. And as you see, there's a red line going through the minimum there, which is the quintessence direction. And this is sloping down, right? And we hope slowly evolving to be consistent with observations. The blue branch is the metastable branch. This excited branch we have for some values of the standard model parameters, some value of quark mass ratios and theta bar. And in the sequester case, by definition, the slope of the curve, the quintessence lines, so this is the slope of the red line and the green line, have to be the same. All right, that's the definition of what we mean by sequestered. It doesn't meaningfully change when we go to the different branch. But then you apply the Swampland de Sitter conjecture in the phi direction to the metastable branch. So this says the slope, the modulus of the slope, has to be bigger than some order 1 coefficient times m quark times lambda QCD cubed over m Planck, or the curvature has to be large. But then once you've done that, for instance, you do the first condition, exactly the same slope and curvature has to apply to the lower branch. But in this case, then you find this is a very steep quintessence field. In fact, it evolves immensely quickly. You can quickly go through. In fact, compared to our current Hubble time, it evolves to deep anti-de Sitter in a fraction, if you put in the numbers for, say, the up quark mass, a fraction of 10 to the minus 43 of a Hubble time to deep anti-de Sitter. Right? So this is completely not a viable situation. Right? This is completely forbidden. So you can't do sequestered quintessence. Right? Once you satisfy the Swampland de Sitter conjecture for the upper branch, the lower branch, you're totally forbidden from living in that vacuum. It just evolves to a big crunch state, basically instantaneously. Okay, and the basic reason for this is the huge disparity in vacuum energy between m quark times lambda QCD cubed and our current CC. So now you can do this, the unsequestered case. With the unsequestered case, by definition, you can imagine the slope in the quintessence direction is changing. It has to actually change greatly between the two cases. But the problem with this is it needs significant couplings of phi to the pion fields. I emphasized to you that the only thing that's changing between the lower branch and the upper branch is pion vevs are turning on. Right? So we have to have the quintessence field coupling to QCD significantly. And now, if you consider radiative effects due to these couplings, they destabilize the required flatness of quintessence potential for the lower branch, unless you allow extreme tuning of multiple terms. It's not enough just to set one term to 0. In fact, you have to set multiple terms to very, very close to 0. In fact, this tuning is significantly worse than that's required for just the cosmological constant. It's not enough just to tune that minimum where the red line crosses the black line to be close to 0. You have to tune a whole bunch of other terms, very, very small, much smaller than radiative correctness too, as well. And moreover, the Swampland says that we can't do as much tuning as in the old picture of the landscape that was, very popular in the mid-2000s, because we have far fewer states near cosmological constant equals 0 in the Swampland, in theories that satisfy the Swampland. So this is really problematic. So I would claim, though this actually deserves further quantitative study, I would claim that it's impossible in the Swampland for theories that self-consistently satisfy the Swampland conditions to tune enough to get quintessence to work in this case as well. So, all right. Okay, now some comments. So first of all, to say this is a leading order analysis. All the issues of metastable states I found here. Right, it says the leading order chiral Lagrangian. There can be extra metastable states that appear in higher order, special values of the couplings. That's interesting. So the regions can be bigger than the ones I've displayed. The regions forbidden by the Swampland conjecture include points with global symmetry. It was the mass ratios going towards 1 that allowed these metastable states to exist. Right, so that's exactly when I turn on and enhance global symmetry. You might be worried that I'm applying the Swampland conjecture to composite fields, pions, and the chiral Lagrangian. So suppose it only applied to fundamental fields, not composite fields like pions. But then we can use our construction, apply to hidden sectors, to, for instance, generate uplifting to non-zero cosmological constant. I mean, I have to say that's logically possible. It's logically possible that it could apply to only fundamental and not composite fields. So I wouldn't really understand how to very strictly delineate the two possibilities, distinguish two possibilities. But if you could do this, then you can use our construction to generate inflationary potentials or uplift fairly deep anti-de Sitter to de Sitter, and it would make the Swampland de Sitter conjecture essentially vacuous. So for the purposes of this discussion, I'm going to assume that's not the case, and it does apply to composite fields as well as fundamental fields. So that was most of the analysis. I mean, the ideas were a little bit different in there, but most of the analysis was old analysis. Let's turn to a different limit of the standard model. Okay. So now I want to think about a different case. So let's look at the case of no light quarks. Right? Is that case similarly constrained by the Swampland de Sitter conjecture? This is particularly interesting as you can achieve this limit in two ways. You can achieve this limit by taking all your chiral couplings to be much, much bigger than 10 to the minus 2 with the electroweak Vev fixed. Or you can fix all your chiral couplings to their current values and take the electroweak Vev to be much bigger than 50 TeV. In either case, we have no light quarks below 1 GeV. So if in case 2, our thinking might lead to a new perspective on the hierarchy problem. We might have a reason why we couldn't have a very large electroweak Vev. Well, what is this theory? So in this limit, the IR theory is a pure SU3 cross U1 theory. There's no matter that links the two gauge groups. That all the matter is heavy. So the two gauge groups are totally decoupled. Well, I'm aware of no argument that U1 EM has metastable states. But in fact, there are lots of arguments, at least in the SUNC large NC limit, that SUNC does possess a rich spectrum of metastable states. As I'll talk about later, it would be nice to have some lattice studies of this issue. They're rather lacking. But these again, old arguments going back to Witten and then to Schiffman and more recent people talking about the spectrum metastables and pure SUN theories. Okay, so what's the basic argument? What is their basic argument? So again, you must have their argument. You must have multiple branches of the potential energy function to reconcile. Well, first it must be a periodic function of period 2 pi in theta bar. But then second, by a detailed large NC analysis, you argue the potential has to have the scaling NC squared times a function of theta bar on NC with its function f being 2 pi 2 periodic. And this is impossible to reconcile unless you have a multi-branch function. So now the ground state potential as a function of theta bar is the minimum over these various branches as a function of theta, where we have this form for these different branches. So if you do that, this is the picture you get these things where each branch has a much bigger period than 2 pi, But altogether, the whole system is 2 pi periodic. So here, the true ground states is this red non-analytic curve at the bottom as a function of theta bar. And then you get these extra branches of the potential which interleave. And Witten argued in his early paper that in the formal large NC limit, NC goes to infinity limit, all these extra critical points were local minima and provide metastable states. Okay. So what are the properties of these states? Well, you can define a topological susceptibility of QCD. So this is just a correlation function of basically the trace of GG joule, the QCD field strength. And the order parameter that distinguishes these various states is exactly the expectation value of this GG joule. So the expectation value in the nth state, right, is theta plus 2 pi n times this topological susceptibility. And we know from lattice studies and from fitting with the experiment as well, this topological susceptibility is non-zero, right? And in fact, for small n states, the lower branches, so n is much smaller than nc, we know what the splitting is between the different states. It goes like 2 pi n squared over 2 times this topological susceptibility. And topological susceptibility is again set by lambda QCD, as you expect. It's of order 200 MeV to the fourth. Okay. Let me not worry about this. It's another way of characterizing. But we care about finite NC. So the overall picture is believed to continue to hold, but now a subset of the critical points become local maxima and saddle points, and a number of the local minima depends non-trivially on theta. So there's been recent studies of this. For instance, there's this nice paper by Aitken et al., which argues there's this rather rich dependence of the number of metastable states and how they vary depending on NC and depending on theta. And if you took this analysis as correct, they do one particular semi-classical analysis, then you'd find that 4-color QCD has a metastable state at theta equals 0, but not 3-color QCD, which is sad, unfortunate. On the other hand, a different semi-classical argument due to Halpern and Zhenitsky a number of years ago does find metastable states at theta equals 0. So literally, again, theta and theta bar equal here because there's no masses, all the matter is gone, right? And this again for NC equals 3 QCD, so real QCD, okay? So we are in the situation, there have been no sufficiently good lattice studies of this question. So we, in fact, don't know the truth. We do not know whether 3-color QCD has metastable states or not. So now it's just possible that 0 flavor, 3-color QCD has metastable states. And if this was true, using the same logic I gave in the previous section, the Swampland de Sitter conjecture could forbid the very large electroweak Vev limit of the standard model. So this is, we've been speaking to Mike Tepper at Oxford, and he's very soon going to be starting a series of investigations of exactly this issue. What is the metastable state structure of 3-color QCD? So we wait to find out what happens. So Miguel, can I have another 10 minutes if that was okay? Because I have some very interesting results on further hierarchy problem issues. Would that be all right?
Yeah, sure.
Okay. Otherwise, we do it in discussion, but I'd like to tell you what these possible other results are. So I think you'll find it fascinating. Okay. So now I want to turn on to a different limit, which is amenable to reliable analytic analysis. Okay. All I'm needing to assume is that confinement and chiral symmetry breaking persists. So let me show you this. This is this paper that's soon to appear. So this is, rather than taking the Higgs mass square parameter in the Lagrangian to be very large and negative, which sends the electroweak Vev to infinity, let me consider the limit of a positive Higgs mass squared. In fact, all I need it to be is parametrically bigger than 1 GeV squared. So this naively implies that V electroweak is 0. Let's see what Swampland de Sitter conjecture might say about that. And what I'm going to do here in this talk is this part now, I'm keeping all the standard model Yukawa couplings fixed. I'm only varying this one parameter, this Higgs mass parameter. But for the moment, let me just do this, the story without the Yukawa couplings turned on. We'll correct that later. For the moment, it's just the gauge interactions turned on. Well, so for m Higgs squared being much greater than 1 GeV squared, the low energy theory consists of SU3 cross SU2 cross U1, because we haven't broken electroweak symmetry by a Higgs Vev, with 3 generations of massless quarks and massless leptons, and no Higgs degrees of freedom. That's gone. We're going to, in fact, integrate it out. So lattice studies indicate that this situation still confines and breaks quark chiral symmetry. So we have 6 massless quarks. So we have an SU6 left cross an SU6 right goes down this SU6 vector unbroken group. Okay, so we have, if this was everything, we would have 35 exact Nambu-Goldstone bosons in this situation, right? And that's the cross-hatched region of this diagram. But the electroweak bosons are light in this theory, all right? So we have to worry about the gauging of those generators. So they're a subgroup of these SU6 left cross SU6 right generators. So we gauge them, and in fact, 3 of them sit in the broken generators, and one of them, U1 electromagnetism in the end, sits outside, it's unbroken, okay? And this gauging of just a subset of the generators explicitly breaks the SU6 left cross SU6 right flavor symmetry. I'm sure Howard, if he's still there, this will look very familiar from old Technicolor days. So, moreover, this condensate, the chiral condensate, which in this case is proportional to the six-dimensional unit matrix, breaks electroweak symmetry. And 3 of the Nambu-Goldstone bosons are eaten, become Higgsed. So what is the consequence of this? Well, the consequence of this is this explicit breaking by electroweak gauging gives masses and a potential to 16 Nambu-Goldstone bosons. You can actually understand why 16 and not some other number, because after everything settles, there are in fact, there's an unbroken exact SU3 situation. Remember, I haven't yet turned on Yukawas, and of course, gauge interactions should treat all generations equally. So there's an unbroken exact SU3 intergenerational symmetry. And so everything must be in multiplets of SU3. And so the 16 Nambu-Goldstone bosons that now get a mass are 2 8s that build together, a complex 8, all right? A complex adjoint of SU3. So what we want to do is we want to compute the potential on that part of the parameter space. We want to compute in this thing the potential function, which is a non-trivial potential function, the 6-dimensional part in field space of the full low energy field space. Right? And so that's easy to do. Again, you use the Cannon-Cohen-Weston-Mino formalism. You write down the pion fields, right? This exponential form. Here, capital Pi is the dimensionless pion field, so without F there. The breaking that gives you the potential is generated by electroweak radiative effects. So here it is. So P left and P right are the coupling matrices for hypercharge and for SU2 weak. And there's an interesting property of these things, which is, of course, SU2 weak is only left-handed. So P right for SU2 is 0. And also the hypercharge matrix on the left-handed guys is just proportional to the unit matrix. Okay. So those 2 properties, in fact, lead to the fact that this potential, later on, they will lead to the fact that this potential goes like G squared times G prime squared times F to the 4th. There's no contribution that goes like, for instance, G squared F to the 4th, or G prime squared F to the 4th, or, G to the 4th times F to the 4th. This is the leading contribution. It has to involve both SU2 and U1 gauging, this potential. So you can study this. There's a unique leading term that involves this gauging. Here it is. This gives a gauge boson mass matrix at U equals 1, so the normal ground state. This thing has these eigenvalues. This is a normal value of sine squared theta W. This factor of 3 is there because you have 3 generations around. And moreover, these masses are small, right? As G and G prime are less than 1, are small, these things appear consistently in effective theory. So now let's see what the potential is. Well, the interesting thing is, as U varies away from 1, these mass eigenvalues change, and therefore, when you integrate them out, you get a non-trivial potential. So you can do that, and in fact, for this SU3 generation case, where you have this remaining SU3 symmetry, it's exceedingly complex. I'll show you some formula right at the end, maybe in a discussion, but it's an incredible pain, which is what we've been spending the last month on. But in fact, there's a much simpler case that demonstrates all the physics. And that's just the 2 generations. So in 2 generations, you just have SU4 cross SU4 breaking down SU4 vector. there are now 6 pseudo-Nearby-Goldstone bosons that pick up masses due to this gauging of the electroweak symmetry. Right, again, a 3 plus a 3, 3 plus a 3, as they go. And we can study that potential very easily and very explicitly. So here it is. You can explicitly parameterize the massive directions. They're pi 1j and pi 2j, so 2, 3 vectors. They're the 6 pseudo-Nearby-Goldstone bosons. And here is the potential. The potential, again, with no Yukawa couplings yet turned on, goes like minus g squared, g prime squared, f to the 4th, and then this open brackets, the square of this sum of these two cosine functions. All right. So as claimed, this vanishes if either of the SU2 weak or U1 gauge couplings are 0. And in fact, I can still use this global SU2 intergenerational symmetry to rotate the axes to V just depends on 3 fields. So I can show you a density plot of what this potential looks like. So here it is. This is, as a function of the 3 fields, what the potential function looks like. And where there's blue areas, there's blue in this very center, and then the other blue areas, these are the local minima of the potential. So these are regions of local minima of the situation. Here's another plot, further rotated with a different color scheme as it extends out. So these are distinguished, these are distinct, physically distinct, with different values of the pion vevs, not related by 2 pi, minima of the theory. Right. So from another perspective, let's consider a plane cut through this thing. Let's consider the plane where I set one particular pion field to 0. And here is the structure of these local minima. Okay. So these are physically distinct minima, which are deep, but currently degenerate. Right? And that's not a surprise, because we have this remaining exact global symmetry of the theory. We've neglected the effect of the Yukawa terms. So of course, we know how to handle that. Here's the Yukawa terms. What we do is, by assumption, the Higgs doublet is massive here, much more massive than 1 GeV. So we integrate it out, and we generate 4 Fermi terms, right, suppressed by 1 over mh squared. And you can look about what terms these give in the Carl-Lagrangian, and they give this rather complicated-looking term in the Carl-Lagrangian that's written at the bottom here, which goes like some unknown order 1 coefficient I, which has to be determined by lattice studies. So it's like the B0 parameter in the normal Carl-Lagrangian, times f to the 6 over mh squared, and then it's a complicated function. But the crucial thing is this complicated function, even if you turn on a single Yukawa, like just the top Yukawa, splits the degeneracy of subsets of local minima. So here's an example. So the dark blue ones are still low minima. They actually have gone down. They've become even lower potential. The ones that are sort of reddish brown in color, they've gone up. All right. So now we split these physically different minima. Incidentally, you get these bands because we've only just turned on one Yukawa in this theory. If you turn on the full Yukawa matrices, everything gets split from each other in some crazy way. But this is just an illustration. You can do another thing. Well, this is interestingly different to the previous case we did, because when we did Yukawas, because before, in this case, before we turn on Yukawa couplings, we already have distinct deep minima due to the gauge interactions, but they just happen to be degenerate at the minima. All right. Now, when you turn on the Yukawa couplings, their sole role is not to generate local minima, but just to split different minima slightly from each other. Right. That's different from what happened before. Previously, Yukawas had to generate both the minima and split them. Right. Now they just split them. So in particular, that means we, in this case, in this limit, when we're considering positive Higgs mass squared parameter, we don't care about the ratios of Yukawas as long as we're not at a global symmetry enhanced point, right? Once you're not at a global symmetry enhanced point, then in fact, these minima are always split from each other, okay? So how much is this splitting? Well, this splitting now goes like Yukawa coupling squared times f to the 6 over m Higgs squared. And the interesting thing is this splitting is much greater than the observed size of the cosmological constant, even for m Higgs squared being m Planck squared. All right. So again, there's this ratio of the splitting between the ground state, all right, which is one of these minima, and this one of these excited states, one of these other higher local minima. That splitting is again much bigger than the observed cosmological constant. So the same arguments we made before against quintessence ruining things applies here. So applying the logic of the earlier discussion, we conclude the entire range where this analysis is valid. Therefore, m Higgs squared being much, much bigger than 1 GeV squared, is plausibly excluded by this refined de Sitter conjecture. Okay, so I'm going to stop there. I want to emphasize there's potentially much more to say. We're hoping to say a bunch more on a lot of different things in upcoming papers, but I'll let you read them in our paper that's soon to be out and ones in the future. So that's all, folks. Thank you.